Okay. So let's start again with Andrea Montanari from Stanford. Who is talking about the first time on matrix, graph, tensor estimation.
Hello? It's better? Yeah. Okay. Yeah, so it would be about a few examples of matrix estimation problems. Okay, so what is this about? Standard estimation theory is about, you have a vector in d dimension, and you take some noisy observations of this vector, and then, you want to reconstruct the vector. In this lecture, I'll focus instead on the case in which you have a matrix. Okay. So this is an object like this, and or perhaps we'll talk a little bit about the case of a vector of a tensor. So this is an object like this. And you are given observations that consist typically in a vector y that has some distribution p that is parameterized by my matrix X. Okay? And the goal is to come up with an estimator of this matrix X set of y that reproduces as well as possible X. Okay, now a couple of remarks. At first sight, there seems to be no difference between this case and this case because you can simply vectorize any matrix. But as a matter of fact, where the difference comes in, the differences come in is for two reasons. First of all, typically we are interested in a class of matrices. So we are interested in a matrix X that is not a generic matrix but belongs to some class. And this class is a subset of all the D1 by D2 matrices. And the way in which we define this class uses very strongly the matrix structure. So actually a typical example that we look again and again is the case in which the rank of the matrix X is small. And second is that the estimation error again exploits in a crucial way, the definition of the estimation error exploits in a crucial way the fact that this has a metric structure. So a typical example is the one in which we measure the quality of our estimation X set by operator norm. Right, so this is just the size of the largest singular value of this matrix. Okay, so these two things make this a problem that is different from the classical problem. And a simplest example of this, simplest example that is useful to keep in mind is the so-called spiked matrix model. Spiked matrix. Let me describe what this is. This is a simple, very simple problem in which you have a matrix X and you observe just X plus noise. Okay? And simple assumption is that the rank of X is 1, and this is, for instance, IAD entries. Okay. So another way to write this, since this is a matrix of rank 1, is to say that this is a coefficient times lambda times a coefficient lambda times uv transpose plus noise, where u is a vector of dimension d1, v is a vector of dimension d2 with norms equal to 1. And you know, this is as IID entry, so we can think, for instance, that Wij are IID with some common low PW. Okay, and okay, this is noise, so we'll assume typically that. Okay, so already in this simple example, you see that. So you know, we used in a crucial way the fact that this is a matrix to say that this is rank 1, and then typically we are interested in estimating either x in operator norm, so having an estimator that has this norm small, or perhaps we are interested even in the singular value, singular vector. Okay. So as simple as this example is, in fact, it's a useful toy model to understand you know, more complicated problems, and you know, I'll visit more complicated problems in the rest of these lectures. So a few problems that I'll talk about will be, I'll talk a little bit about sparse principal component analysis. I'll talk a little bit about, more than a little bit about a closely related problem that is the hidden or planted clique problem. I'll talk a little bit about you know, the tensor version of this, I think, that is sometimes called tensor principal component analysis, and perhaps I'll talk about metrics and tensor completion. Yeah. So I don't really know how much of this I'll be able to cover, but you know, I'll try to do a little bit of this. And from another perspective, I'll try to describe a few tools that are used in this area and explain these tools. What are these tools? I'll talk about linear algebra. Talk about a little bit of random matrix theory. So these are obvious that they play a role here. Of course, algebra, you know, even in linear algebra, even in the definition of the rank, plays a role. Random matrix theory, well, you know, this is a matrix, a noise matrix with IID entries, so it's important to understand its eigenvalues or singular values. When you go try to design algorithms for these problems, there is a class of algorithms that are just spectral algorithms, and you can understand them basically in terms of linear algebra. There is another class of algorithm that is very useful, and these are semi-definite programming relaxation. So I'll talk about, in particular, SDP hierarchies. So these are you know, more sophisticated algorithms that just simple spectral algorithms. And finally, I'll talk about a class of algorithms that are very natural when you look at graph version of these problems, like the planted clique problem or the hidden partition model. And these are message passing algorithms. Okay. So the first lecture today, I'll mostly focus on these two, and hopefully I'll be able to, you know, give all the background on these first two dots in the first lecture. To some of you will be, you know, very boring because you know all of this stuff. So Stefan, for instance, should be given. But we'll try to get through all of it, and then in the next lecture, perhaps we'll go to more sophisticated stuff. Okay, hi, Monte. So from another point of view, to some of you, this will be very, very fast because I teach a quarter-long class on these topics in Stanford. So I'm trying to compress this class in 4 days. So please stop me if things that I'm saying don't make sense. Huh? Don't hesitate to interrupt me. Okay, so let me start with linear algebra. So a very quick reminder. So first thing that we use a lot, it's of course the singular value decomposition. So you have a matrix M. And we all know the singular value decomposition as the form sum over I 1, 2, okay, let's say R, sigma I, ui, bi transpose, where the sigma i's will be the singular values. So sigma 1 bigger or equal sigma 2 bigger or equal sigma R positive. R is the rank. And the u's and v's are vectors that are orthogonal or orthonormals. Okay, so ui I less than R are orthonormal. And the same for the right singular vectors. Okay, and of course, if M is equal to transpose, so M is symmetric, we replace this by the eigenvalue decomposition. Okay. Now, the single most important fact about singular values is that they satisfy a variational representation. And the representation is the following. Okay, let me define SND. So this is the set of all subspaces of Rn of dimension D. Okay. This is also the Grassmannian. So the kth singular value of the matrix M has two dual representation. You can see it, look at it as the minimum over all spaces in Sn. Okay, let me see. N minus k plus 1 of the max over all V in capital V of norm 1 of what? Of M times V. So the first singular value, while this is all the space, so it's just the direction in which M dilates most any vector. So take any unit vector, look at how its norm increases. The maximum of this norm is the singular value. The kth singular value, well, what you look at all subspaces. So there is an adversary that tries to look at the subspace in which the matrix is the smallest in norm, and then you look at the norm within this subspace. An equivalent, an alternative representation in which you interchange the max with the min is that this is the max over all subspaces Snk of the mean over all V in capital V with norm of V equal 1 over V. So this is saying, the dual, this is giving you the dual statement, somehow. The minimum singular value, while this corresponds to taking k equal n, okay? So in this case is is you are looking at the direction in which the matrix M expands the most, the least. And if you want to look at the kth, well, you want to look at the subspace that helps you the most, and then within subspace, look at the minimum singular value in that subspace. There is, okay, I will not prove this fact, but there is a useful fact that follows from this, and that's very insightful, is the following. It's very insightful for the kind of problems that we are interested in, and is the following. If you take any such matrix, and let's say that for simplicity, sigma k is non-degenerate, so this means that the kth minus 1 singular value is strictly bigger, and the kth plus 1 is strictly smaller. Then if you do this optimization problem, so suppose that you try to solve the following optimization problem. Try to find the matrix that approximates M the most in Frobenius norm, for instance. Overall matrix is X of rank at most K. Then the solution of this problem is unique and is given by X star, just the sum over the first K object. Okay, so this is these three statements are not hard to prove, and if you never saw them, it's a fun exercise to do. Okay. Now here I introduce something that is the norm of the matrix. This is a useful thing to have. So we'll use two norms basically in this class. One is the Frobenius norm. So the Frobenius norm of a matrix M, or of a matrix, okay, let me write A, is what? It's just the norm of the matrix is if you forget that it is a matrix. If you stack all the entries as a vector and you look at it as a vector. Okay, so you can also write it. This is the sum over I and j, aij square. This is particularly interesting because it's also the norm associated with scalar product that will denote AB. So this is just the scalar product between the two vectors that you're obtaining by vectorizing the matrices, okay? Or it's also the trace of A times B transpose, okay? There is another norm that is very useful. This is the operator norm. This is already used up there. The operator norm of a matrix, I'll denote it like this. This is just the size of the first singular value. Okay. Okay. It's obvious that this is a norm from Euclidean geometry. It's not entirely obvious that this is a norm, and in fact, I'll give you a statement of this form in 5 minutes. In particular, it's not obvious that it satisfies triangular inequality. Okay, so let's see. Okay, so hopefully all of this was more or less well known. There is one, so all of this fits any undergraduate class in linear algebra. There is one part that is normally not taught in undergraduate linear algebra, and it is perturbation theory. So what is perturbation theory? Perturbation theory deals with the following problem. You have a matrix A, not. Okay, again, say that this is M by N. And this is simple in some sense. Okay, so you understand very well its singular value decomposition. And now what you want to look at is a new matrix A1 that is A0 plus some perturbation. Okay, so this is my perturbation. So you understand well the singular spaces, singular value of A0, and now you want to understand what are the singular vectors and singular value of A1. Okay? So the general question is, are singular values vectors of A1 similar to those of A0? Okay, so this is in itself, a whole area of mathematics that, yeah. Sorry? Simple. Well, it's singular values or it's singular vectors. Okay, that's what I mean by simple. Really, you know very well what are, or you know something about this singular vector and singular values. So this whole area was developed, to its full glory in the 50s, where people were very interested in quantum mechanics, and this typically was a Hamiltonian of a quantum mechanical system, and then this was a perturbed Hamiltonian. So this was an Hamiltonian in which electrons don't interact with each other, and this is a Hamiltonian in which they interact with each other. And so you understood very well the physics without interaction, and then you wanted to understand the physics with the interaction, right? That's what. But we'll see many examples of this thing. All right? Now this is a huge area in itself. What I'll use is only two very simple results. We don't need anything else. And the first result is Weil's inequality. Weil's inequality, what does it tell you is the following: that sigma for any singular value, so you compute the difference between the ith singular value of A0 and of A1. Okay, so you want to see how much this changes. And this is saying just that this is very simple. This is upper bounded by the operator norm of W, of the perturbation. All right. So you understand what are the singular values of A0. And now you know that if your perturbation is small, the 1 of A1 cannot be too far. Notice that this in particular implies that the operator norm satisfies triangular inequality. Okay, so let me prove it. Just as an exercise, it's very easy, but somebody says every talk should have a proof and a joke, and they better not be the same. Okay, so this is something that I can do with confidence. So you want this. So it's just an exercise in using the variational principle. Okay, so I'll write this as the max over V in S and I, mean over V in capital V of norm 1 of what? Of A1 times V, of course. Okay, so this is what I wrote before. So these two variational principles, for somebody who wants to do theory or write papers like me, how do you use this variational principle to get bounds, right? One writes it as a mean, the other as a max. So you use that for doing lower bounds and that for doing upper bounds, right? And the way you do it is that you just guess what is capital V, right? There is this messy variational problem, you guess the capital V, and this gives you a lower bound. You guess the capital V, and this gives you an upper bound. So I brought that one, so I want to do an upper bound. Right? So I want to do a lower bound. So I want to guess the max. I want to guess the subspace V. What should I take as subspace V? What should I take as subspace V? Okay, there is some white noise coming. So I want to bound the, I know very well A0. A0 is something that I know and love. I know its eigenspaces. It's singular spaces. So what should I use? The singular space of A0, right? So I should take V. So take V, let's call it, let's give it a name. Let's give it a name. Vi of A0. Okay, so this is the span of V1 of A0, Vi of A0. This is my notation for the top singular vectors. Okay, so you get a lower bound if you do this. Okay. Now we know what is A1. A1 really is A0 plus W. So this is really A0 plus W times V. 2. Okay. Now I want to lower bound this guy. So what I can use is triangular inequality. So if I do triangular inequality, I get A0 V2 minus W V2. This is upper bounded by the operator norm of W, so you get the mean over V in Vi of A0, V norm 1, of A0V minus W operator norm. And now I'm in great shape because this is a constant, and this I know how to minimize because, again, by the variational principle, this is just minimized at Vi of A0 and gives you sigma I of A0 minus the operator norm of W. Okay. So this gives you one side of this inequality. You exchange A0 and A1, and you get the other side. Okay, so very easy. Okay, so Weil's inequality. Okay, now I will erase this proof, if okay with you. Can I erase? Can I erase? Can I erase? Yes, I'll erase it. So Weil's inequality tells you something about the singular values, but often what we are interested in is in singular vectors. Right? So we want to understand how noise moves singular vectors. Again, this is, there are lots of results in this field, but the theorem that I'll state, what we need is just the following theorem, and this is the most used in this area, Vedin's theorem. Okay. So Vedin's theorem is about not singular vectors, but singular spaces. So the space spanned by top k singular vectors. Why singular spaces and not singular vectors? Because singular vectors can be more sensitive to noise. That's whole bunches of them, whole singular spaces. Okay? So I need to give you a notion of a distance between singular spaces, and one way to do is the following. Okay, I'll denote. So I have A0 and A1. I'll denote by P K A. This is the projector on the span of B I A I less equal than K. So take the top k singular vectors and look at the span of those vectors. Call the orthogonal projector that span Pk. I have two of them. I have the 0 here that is for the unperturbed matrix, and the 1 here that is for the perturbed matrix. Okay, so this is what we'll use to define a distance. So Vedin's theorem, okay, I'll state a slightly simplified version of Vedin's theorem, but the original theorem is a bit messy to parse, so I'll give you this simplified version that says the following. Assume that the perturbation is not too big, and not too big means the following, means that it must be smaller, actually strictly smaller, than the difference between the kth and the kth plus 1 singular values of A0. Okay, so this is the crucial thing. What does it mean that a perturbation is big, vis-a-vis, the kth singular space? Well, it's big if it is big compared to the gap between the kth and the kth plus 1 singular values. Okay, so if this is true, then the following happens. Okay, then you look at how much these spaces move, and this you measure in the following way. You look at 1 minus P0 k times P1 k, and you look at the operator norm. All right? So why is this a difference, a distance? Well, it's not really a distance in technical sense, but why this measure how much these two subspaces are close? Well, if the subspace doesn't move at all, then this projector is equal to this projector. So this whole guy is the projector on the orthogonal complement of this space. So the product of these two matrices is exactly 0. Okay? So if the two subspaces are the same, this product is exactly 0. And of course, this product is always between 0 and 1, right? Because the operator norm of a projector is at most 1, and the operator norm of a product is at most the product of the operator norms. Okay? So you look at this metric between the two subspaces, and Vedin's theorem says the following. This is less than W op. So there is the gap. All right. So it says that if this perturbation is small, this distance is small. And what matters really in this expression that I gave you here is really the ratio between the size of the perturbation and the size of the gap. To emphasize this even more, I can do the following. Let's say that the operator norm is less than 1/2 of the gap. If it's less than 1/2 of the gap, then you can substitute here. Then, if you have the stronger assumption, the left-hand side is less than 2. I brought this just to, emphasize that until you have the perturbation of the size of gap, Vedin's theorem gives you something non-trivial. But in reality, most of the application, if you are happy to lose a factor 2, this is 1/2. If you are happy to lose a factor 2 in the size of the perturbation, this is even cleaner. It tells you really that the amount by which the singular space shifts is really the size of the perturbation divided by the gap times a factor 2. Okay, excellent. Okay, so why should we compare this to this gap? Why it makes sense that the gap enters this expression? Any suggestion? Yeah, so if the gap was 0, right? If the gap was 0, if the kth singular value is equal to the kth plus 1 singular value, then it's not really defined which one is the kth and the kth plus 1, right? Suppose that you take k equal 1, okay? So you are interested just in the first singular vector. So the first singular value is equal to the second singular value. Really, there is no well-defined notion of what is the top singular vectors. The top singular vector is V1 is as good as V2. So even a zero perturbation can give you two orthogonal answers, okay? So it's kind of clear that when this is zero, then you cannot tolerate any perturbation. And the other thing that is obvious is somehow that what you get on the right-hand side here should depend only on the ratio of W and the gap, right? Because if I double W and if I W is 0, the singular spaces don't change, of course. Okay. So let me see what this gives you in a special, oh, perhaps I'll take more space. Well, perhaps I'll erase this one. Okay, let's look at a special case, that is the case k equal 1. So you have just one singular vectors, and let me call, let's say, V0, the top singular vector of A0, and V1, top singular vector of A0, and V1, the top singular vector of A1. And let's see what this mysterious distance is in that case. If I call that matrix Q, this is just 1 minus V0 transpose times V1 transpose. Okay, so if I compute Q transpose, this is just, let's say, 1 minus P 0 times V1 transpose times 1 minus P1 0. Okay. So if you compute the operator norm of this guy, so the operator norm of Q is just the square root of the operator norm of this fellow. And this is just a rank 1 matrix, right? It's a vector times its transpose, right? So this is just the square of the norm of the vector 1 minus P0 times V1 square. Okay, so this whole business is just what? Okay, so just by Pythagoras theorem, the projection orthogonal to 0 is just 1 minus the projection along 0. Okay, so if I take square root of everything, so in this case with k equal 1, Vedian's theorem tells you something about, basically this is the sign of the angle between the two vectors. The absolute value of the sign of the angle between V0 and V1. Okay. Any question? Okay, very good. Okay, now the sound. All right, so basically I did all that I wanted to do in linear algebra. Okay, we did it in half an hour. Okay. Now I'll do, perhaps half an hour of random matrix theory. So what I'll do is that I'll state just a few, I'll explain just a few very simple things, right, that you can do basically without having any tool. And then, sometimes I will cite things that are more sophisticated, but without explaining how you get them. And perhaps we'll come back to this later in a few days, perhaps. So what I want to do just here today is just a random matrices with IID sub-Gaussian entries, okay? So I need a couple of definitions for that. This is extremely simple. So we have a random variable x. A real, just a number, random number, is tau square sub-Gaussian if the following happens. For any lambda a real number, okay, center the random variable, and then look at the moment generating function. This is bounded by the moment generating function of a Gaussian with variance tau square. It's upper bounded by this. So see, for large lambda, the moment generating function is dominated by large deviations of x with respect to its mean. So this statement is a statement basically about the tail of this centered random variable. Okay? So one way to get that explicitly is to prove a little lemma that says the following. If x is tau square sub-Gaussian, then the following happens. Probability that x is bigger or equal than its expectation plus an amount t for any t is upper bounded by e to the minus t square over 2 tau square. No? So this is a statement about the upper tail, but of course this definition is invariant if you change x minus its expectation is in its opposite. So if I put a minus sign here, it doesn't change. So you can get the same statement for the lower tail. Okay? So the same bound holds if you write this. The same thing. And basically, these two, I will not prove this, it's just a little exercise, but these two are equivalent in the sense that if you assume this, and sometimes people give this as definition of sub-Gaussian, you get this bound of the moment generating function possibly with worse constants here. Okay? So this implies, now I don't remember what is the constants, but these two property implies, let's say, 3 tau square sub-Gaussian. I think 3 is sufficient. Surely it's not the best. But. So you can say that the sub-Gaussian is something that has moment generating function upper bounded by 1 of the Gaussian, or it has tail probabilities upper bounded by tail probabilities of a Gaussian. Okay. Okay, very nice. What about a random vector? Let's say in d dimension. Doesn't matter. So a random vector x is square sub-Gaussian if for any u with norm of u equal to 1, x times u is tau square sub-Gaussian. Again, this is similar to what you say in the case of Gaussian random variable. What is Gaussian? A Gaussian random vector. It's a vector whose one-dimensional projections are Gaussian. And here I'm saying is a sub-Gaussian random vector is by definition something that has one-dimensional projection that are sub-Gaussian. So why it's very easy to work with sub-Gaussians? For many reasons, but one is the following, that whatever you do to them, okay, not whatever, but you can be very bad towards them and they stay sub-Gaussian. So for instance, an important property is the following, that x1, x2 are two independent sub-Gaussian two-square random vectors. Then you can concatenate them. So what I mean by this is just the vector of double length that you obtain by putting x1 and then x2. x1 x2 do not need to be the same length, but if one is d1, the other is d2, you form a vector of length d1 plus d2 by concatenating them. This is two squares of Gaussian. Again, if tonight you cannot sleep because it's too hot and you never saw it, prove it. Or I don't know. Easy consequence of this, again, is that, of course, if you have xi bunch of sub-Gaussian, two-square sub-Gaussian random variables, then the vector x1, xn is also two-square sub-Gaussian. The important thing here is that this constant doesn't change. So you can put together any number that you want. And third property, okay, if x1, x2 independent, so these have to be independent, of course. Independent. Then x1 plus x2, then this is 2 squares of Gaussian. Exactly like with Gaussian, when you add, the variances add up. Okay, where is Monte? Okay. So with these very simple tools, we can prove a very simple but very useful theorem about random matrices. And the theorem says the following: take a matrix that is of dimension, say, d1 plus d2, and say that this random matrix is two squares sub Gaussian. what I mean by this, I really mean that if you vectorize it, it's a 2 square sub-Gaussian vector in the sense that I described above. Okay? For instance, okay, so as a vector. One example of such a matrix is a matrix with independent entries that are themselves 2 square sub-Gaussian. But it could have independent rows or independent columns, doesn't matter. Okay? Okay. Then, for any s bigger or equal than 5, if you look at compare, x to its expectation in operator norm, or take the maximum singular value of x minus the expectation, and claim that this is small, namely the probability that this is bigger than s2 times square root of d1 plus d2 is upper bounded by e to the minus s square over 5 times, say, d1 plus d2. All right? So basically, this is saying that this difference is of order tau times square root of the dimensions of the matrix, or square root of the maximum dimension of the matrix. Okay? So there is one part of this formula that is kind of trivial. Of course, if you scale tau by 2, if you scale the matrix by 2, its norm will be scaled by 2. So this norm must be proportional to tau, if you get any bound at all. What is really surprising here, if you never saw this, is that you get the square root of the dimension. This has very far-reaching consequences. What it's telling you, one second, is that a matrix that is d by d and has entries of order 1 can have, what is the maximum operator norm that it can have? Take a matrix that is d by d, and all entries are, say, bounded by 1. What is the maximum operator norm that such a matrix can have? Log d. No. D square. Can it have norm d square? Let's do a vote. Can it have norm d square? Let's vote. No. Can it have norm d to the 0.4? Okay, I have zero reactivity here. Yeah, it can. The maximum norm that it can have is d. So if you take a norm d, a matrix d by d, and all entries mij are bounded by 1, the maximum norm operator norm that it can have is exactly d. What is such a matrix? It's just a matrix that is everywhere equal to 1. If you have this matrix, etc., this matrix has norm exactly equal to d. Why? Because it has, okay, there are various ways of seeing it, but this is one eigenvalue, or one singular value, that is equal to d. Just hit the all one vector with this matrix, and you get d times the all one vector. Okay? So in general, a matrix that has entries of order 1 has a norm that can be as big as d. So this theorem is telling the following, that if instead of ones you put plus minus 1, with 0 expectation, you put IID plus minus 1 with 0 expectation. Now, plus minus 1 is a sub-Gaussian random variable. That should be clear from definition, but we'll see it again. Then its norm, it's only square root of d. So, this is very counterintuitive in a sense. A random matrix has a norm that is much smaller than the maximum norm. Most matrices have extremely small norm. Sorry?
The matrix with only ones is also in the set of the matrix
Right. I said if you put IID plus minus 1s, so you put a random plus minus 1. So if you start doing simulations, generating matrices, if you go over all matrices d by d, and you fill them with all possible 2 to the square way with plus minus 1, and then plot an histogram of the norm, what you'll see that the norm is like this. Can be between d and 0. There is one case in which it turns out to be d. Actually, two cases, because it can be all plus 1 or all minus 1, but most of them are actually around square root of d. Okay, so the histogram looks like this. All right. Okay, there is an easy proof. Okay, of course, much more sophisticated things are known about this type of matrices, but I'll just prove this fact with a very simple proof. And the proof goes by a method that is called the epsilon net method. This is a method that is worth learning because it never gets the right, the sharp bounds, the sharpest possible bound, but always gets you something. Always gets you something. Almost always gets you something. Okay, so without loss of generality, you can always assume that the expectation is 0. And then other notation, I'll denote by BR, BDXR. So this is the ball in d dimension with center x and radius r. Okay? So what I want to do is that I want to upper bound the probability that the operator norm of this matrix is bigger than t. Okay? This is what I want to do. I want to, expectation is 0. I call this t. I want to upper bound the probability that the operator norm is big. So how do I do it? Well, I learned one thing today. I learned that this is the maximum singular value, and the maximum singular value has a variational representation, right? So let's write the variational representation. So the way I brought the variational representation was max over all d of x d. Okay? But remember that the norm, the norm is just the maximum of all the scalar products. Okay? So this is also the max of u x b. So this is the max over all u in the ball center at 0 in d1 of radius 1, and of b on the ball in d2 of radius 1 of what? Of u x d. I want this max to be bigger than t. Okay, fine. All right, this is great. Now, what is the probability that a max is, what is the event that the max is bigger than t? Is the union of the event that any of these things is bigger than t. So there is one thing that I learned, I don't know probability theory, but there is one thing I learned in kindergarten, is that probability of a union is less than the union of the probabilities. And now I'm going to do something. Okay, let me write it like that. All right. Now I have to compute this probability, right? How do I compute this probability? I have no idea But I recognize that I can write the scalar product as x times the matrix UV transpose. Yeah. It's the same. This is just x transpose times trace of x transpose UV transpose. So it's the same as UX V transpose. It's just the fact that the trace can be permuted cyclically. Fine. So what is this? This is just an ordinary scalar product, I told you. It's the scalar product between the vectorization of this and the vectorization of this. This is the usual Euclidean scalar product. Now you have a tau square vector that is multiplied, a tau square sub-Gaussian vector that is multiplied by something that is of norm what? Well, what is the Frobenius norm of UV transpose? Frobenius norm. Well, if I compute the square of it, this is the trace of what? Of V U transpose U V transpose. This is 1, and this is 1. So this is 1. All right, so I'm multiplying a vector by a vector of norm 1. So the definition of a multiply it by a vector of norm 1, it's a sub-Gaussian random variable. So this is a tau square sub-Gaussian random variable. Okay? So I get a nice small probability. And now I have just to sum over all vectors U and V. Somebody is laughing. Somebody knows the end of the joke. So what is the problem with that? Is that there is too many vectors, right? I started with something crazy because I'm summing over all vector on the balls, and even the notation is wrong, right? Because it doesn't make sense to write a sum over an uncountable set. Okay, but we are very persistent. So what we'll do is that we'll follow the same argument but replace the ball by an epsilon net. So what is an epsilon net? If you take the unit ball in the dimension, so it's an epsilon net. It's just a subset such that if I let me just write like this. If I do the union over all the point in the net of the balls of radius center at x of radius epsilon, this contains my original ball. So I'll approximate the sphere, the ball, by something much smaller. Well, what is nice about epsilon net is nice that they obey these two things. First claim is that there exists an epsilon net of size meaning of cardinality less than 1 plus 2 over epsilon to the 2 to the d. Okay? All right. So you can cover with finitely many balls. And in fact, finitely many means just some constant to the number of dimensions. And why is that? OK, let me show it with a picture. OK, so you have the unit ball. So this is the ball centered at 1. And then what I'll do is just I'll follow the greedy algorithm. What is the greedy algorithm? I just pick a point. And I'll draw a ball of radius epsilon around it. And I'll put it in my net. Now I pick a second point. There are two options. I choose it inside the red ball or outside the red ball. What should I do? Outside, right? It's very stupid to. So I take it outside. And then I repeat. And so on and so forth. At some point, I will stop with this process. Now I have to count how many points do I have. How many points did I put in my net? Now I observe the following. The two red balls must intersect, but any two centers must be at least distance at least epsilon. Why? Because I never did the silly thing of putting a point inside. So if I take a ball around of radius epsilon over 2 around each of these center, these blue balls are disjoint. Okay? So, okay, if you want to play like you know a lot of stuff, you say that a maximal epsilon net is an epsilon over 2 packing, meaning that ball of radius epsilon 2 are a packing. They don't overlap each other. Now, it's a packing of what? It's a packing of the sphere of radius 1 plus epsilon over 2. Because I might have done sometimes the thing of putting a center here, and so the ball goes a little bit outside. So how many balls did I do? Well, it's the volume of this object divided, is at most the volume of this object divided by the volume of this object. All the blue balls don't intersect, so there is at least most. End of story, right? Because the volume is what? Is radius of times radius to the d times some constant that nobody ever remembers. But I don't need the constant because I'm taking the ratio. Okay, so this is claim number 1. Claim number 2. Okay, I will not prove this. So this is exercise. If you look at the operator norm of x, well, we know that this is the max over u in the ball and v of the ball is this. What if I restrict, let me write nd. What if I restrict this u and v to be in an epsilon net? Turns out that this already gives me an estimate of the operator norm in the following sense, that this is upper bounded by this. So this is a linear algebra fact, or a counting fact. Okay, so what happens with that? Happens that you can repeat exactly this proof, except that you lose a factor 1 minus 2 epsilon in the t there. Okay? Instead of putting here the maximum over the ball, you put maximum over the epsilon net, and you lose a factor there. But now you have a finite number of points. So what you get if you repeat that argument, you get that the probability that the operator norm is bigger or equal than t is less or equal than what? Then the size of the product of the size of the two epsilon nets, which is 1 plus 2 epsilon to the d1 plus d2, because I take the union bound over u and the union bound over v, times the probability of any of these guys. And I lose another point. I lose because of this factor. So this gives me an extra factor 2 epsilon. All right? But now what's important? What's important is that I don't care about constants. So I'll just take epsilon equals some fixed number, 1 over 10 or 1 over 5. So what you get is here you get some number, 20 to the d1 plus d2. And here you get another number, t square, let's say, what? 1 over t square over 8 2 square. E minus. And now what you want is that you want this guy to kill this factor. When will it kill this factor? When t is bigger than 2 square root, let's say, 100 2 times square root of d1 plus d2. Then this goes to 0. Now, if you spend, so when I brought the notes that perhaps Gabriel distributed, I spent, this is for my class, I spent, 30 minutes trying to optimize the constant, which is shameful. But in the end, you get just nothing. I mean, you get a better constant. So any question about this proof? Yeah.
So what happens for other norms, for the Frobenius norm, for example?
Well, the Frobenius norm is a much simpler object, right? The Frobenius norm so if you have IID entries, this is the sum of IID numbers. So this will be about d1 times d2 times the expectation of this guy. So, okay, so this actually is it's an interesting fact. So this is what? This is d1 plus d2 times, say, the second moment of this. Let me call it sigma square. So let me say that E of xij is equal to 0, and E of xij square, the variance, is sigma square. So the Frobenius norm is what? Is d1 times d2 times sigma square. Okay, now I want to make an observation about this, because now this brings up an interesting fact. The Frobenius norm is invariant under change of bases. So because of that, you can first reduce to the singular value decomposition. So this is the same as the sum over I1 to R of sigma I square. Okay? Where sigma I are the singular values. So now if all the singular values are of the same size, so let me assume for a moment that D1 is of the same order as D2, that is of the same order as R. Okay, let's call this order D. Okay, then this says that D times 1 over D sum over I sigma I square is equal to D square sigma square. Okay, and if I simplify a D, I get this. So the average singular value, or the root mean square average singular value, is of order sigma times square root of D. Okay. Now, if you have a distribution of the entries in which the variance is of the same order as the sub-Gaussian constant, for instance, a Gaussian random matrix. A Gaussian random variable is really Gaussian random variable, but with the parameter tau square, sub-Gaussian with the parameter tau square that is equal to the variance. So if sigma equal to tau, so if the variance of the entry is the same as the sub-Gaussian entry, or of the same order, then what you obtain is that the average singular value is of order tau square root of t. And this is, of course, less than the maximum singular value. But on the other hand, we prove that this is less than tau square root of t. So this argument says that our upper bound in this setting is basically optimal up to constant. Now, it's not optimal if these two are very different. In which direction they can be very different? Well, this cannot ever be smaller than this, but this can be much larger than this. So you can have variance of order 1, but very heavy tail. I mean, tau can be infinitive and then sigma. But for nice, very nice distribution, our argument is optimal up to constant. Any other question? All right. Okay, so 15 minutes, what I want to do, I'll do perhaps I'll start at least one application of this result. So let us look at what this implies for this simple model that I defined before, that is the symmetric spiked model. The spiked model was what I said. I'll look at the symmetric version, or spiked matrix model. So what is this? You have a matrix Y that is your observation. So this is an n by n matrix. And this is lambda v transpose plus W. And W is noise. It's sub-Gaussian noise. And to be definite, so V is of norm 1. So this parameter lambda is basically, this is noise. And this parameter lambda is really the signal to noise ratio in a sense of this model. And to make things simpler, okay, it doesn't matter really for most of the calculations, but I take W to be a Gaussian orthogonal matrix, a matrix from the Gaussian orthogonal ensemble. So what does it mean? It means the following, that Wij, I less or equal than j, are independent with Wii normal 0 2 over n and Wij normal 0 1 over n for I less than j. So for the calculation that I'll do, this doesn't really matter. You know, the precise distribution, it matters just for one thing that I will say at the end. But I think it's useful just to fix an idea. Above diagonal, I have IID entries that have variance 1 over n. For some reason, on the, the convention is putting 2 over n on the diagonal. This doesn't matter again. You can put all 0 on the diagonal. One reason why it matters is that this particular definition makes the matrix orthogonal invariant. That is, you can do a change of basis and the distribution doesn't change. Okay. One way to see it is to write equivalently. So if you do calculation with this type of matrices, sometimes it's convenient to represent them in different ways. Again, I will not use this fact here, but I'll tell you. You can write this as 1 over square root of 2n times G plus G transpose, where now Gij, this is a symmetric matrix, I should tell. So you fill the entries above and the entries below the diagonal are completely determined. So Gij now is a Ij in n. These are now all IID normal 0, 1. if you generate, way to generate, this is, if you want, the way you generate such a matrix with Python or with R, whatever language you use, you generate a vector, you change the dimension of vector, and add the matrix plus its transpose. So this is a GOE matrix. Now what I want to do with this matrix, I want to estimate V. So what do I want? I want an estimator V hat. What is an estimator? It's just something that takes a matrix as input and splits a vector. And you know, for y gives V hat of y. And this has to be as close as possible to V. So how do I do it? Well, the simplest idea is the following. So what is the idea? If lambda is infinity, or equivalent to W is 0, then what you want to do is take V hat of y equal the first eigenvector of y. All right? Why? Because this gives exactly V. If there was no noise, this would be just a rank 1 matrix. So if you take just the first eigenvector of this rank 1 matrix, this will be exactly V. So you are done. So what we'll do is that you'll do the same. So what about so in this case, W different from 0. So now what we have is this estimator. So we are computing the first eigenvector of this matrix. And we want to compute how close it is to V. Now this is exactly the setting of perturbation theory, right? We have a matrix that is this one that we understand very well. It has one eigenvalue that is equal to lambda, and all the other eigenvalues that are equal to 0. One eigenvector that is equal to V, and the others we don't care. Right? And we perturb it. And now we compute the eigenvector of the perturbed matrix, and we want to compute how close it is. So by Wedding what tells you? Tells you something about the distance between the first eigenvector of the perturbed matrix to the first eigenvector of the unperturbed matrix. Right? What is the distance? So if you remember, we computed explicitly the distance in the case of a rank 1, k equal 1. And it was exactly 1 minus V hat V square. This was the operator norm of 1 minus P0 times P1. And Wedding theorem tells me the following. This is less than somewhat. We said that this is less than 2 times the operator norm of the perturbation divided by the gap between the first eigenvalue and the second eigenvalue of the unperturbed matrix. What is the first eigenvalue of the unperturbed matrix? Lambda. What is the second? 0. So you get lambda. And this is true as long as this makes sense. So if the operator norm of this is less than lambda over 2. All right, so we can invert, sometimes it's nicer to state this in terms of the scalar product. So this is the form in which you find this type of result for this problem. So if you invert this, you get V at V absolute value. Notice that, okay, bigger or equal then 1 minus 2 operator norm of W divided by lambda. So there is a 4, a square, a square, and a square. Okay, so what is now the operator norm of this matrix? We know, we proved that the operator norm of this matrix was bounded by some constant. Now we did it, okay, we did it for, so this is a matrix with IID entries above the diagonal. So all the entries of above the diagonal form what? Form a 1 over n sub-Gaussian random matrix. So W is 1 over n sub-Gaussian. Well, not quite, because there is the entries above the diagonal and below the diagonal that are slightly dependent, but you can always see W as the lower triangular plus the upper triangular, and you will lose a factor 2 or some such factor. 3, 4, whatever. So if you do the calculation, you get at the end of the day that this is less than some, the sub-Gaussian constant, so this is some 10 over square root of n, times square root of the dimension, square root of n. So this norm is a constant. Okay, actually the 4 goes here. Okay? So you get, if you substitute that here, you get 1 minus, again, some other constant that now I don't know. If you write 4 over lambda square. So I'm not paying attention to the constants, and I wrote them in my notes on the flight. I could start writing C's everywhere, but I think this clutters a little bit things. I hope they are correct, but it doesn't really matter for what I'm doing here. Okay, so this is what is this saying? It's saying the following. It's saying the following, that if you look at the scalar product between the true signal and your estimator as a function of lambda. This is, I don't know what, but for lambda bigger than some value 2, this is lower bounded by something and converges to 1. Turns out that in this specific example, people computed exactly what is the limit of this scalar product, and it can be proved that the limit n to infinity of v at v is exactly equal to square root of 1 minus 1 over lambda squared. So it's something like this. Okay, let me write it in a different color. So it has a phase transition at lambda equal 1 that is known as the BB-AP phase transition. And this is for the initials of Baik, Benarus, and Péchet, who first found. So they use some random matrix theory to compute this thing, but basically we obtain up to constant the same behavior, which is nice given that we did it in 10 minutes and without thinking really hard. Okay, so one question is, can you do better than this? So if you approach this question from a statistical point of view, or from estimation theoretic point of view, is, okay, you came up with this estimator But does anybody tell you that this estimator is the optimal thing to be done? Perhaps I come up with something very sophisticated, like take the first 10 eigenvectors and then run this very messy combinatorial algorithm and this bit. Turns out no. Turns out that you cannot do better. So in fact, for lambda, any estimator is asymptotically orthogonal to V. So any estimator is basically uncorrelated to V in the limit. In fact, more of that is true, more than that is true. In fact, the following is true. Consider the simpler problem. So call P lambda the law of Y. That is, you generate Y in this way with V uniformly random. You take a vector V uniformly random on the sphere and compute lambda VV transpose plus W and call the law of the signal lambda. Now a question is, can you distinguish this from P0? So can you recognize that there is some signal? Somebody gives you a matrix. It was either generated with a signal or not with a signal. And it's playing a game with you. It asks you, is there a signal here or not? So this corresponds to computing the total variation distance of these two laws. And turns out that for lambda less than 1 as n to infinity, okay, this is less than a constant less than 1. For lambda less than 1. So for lambda less than 1, not only it's impossible to estimate, but it's impossible to say with absolute, with certainty, with high probability, is there a signal or there is not a signal. Okay, so this simple spectral estimator in this case, it's very successful. It gets you the exact optimal phase transition, not only up to constant, but the right number 1. Okay, now our analysis was a bit quick and we didn't get the right threshold. But any question? If not, it's all for today.